Hi, this video is a walkthrough of the code to solve problems for anomaly detection. So basically we're discussing chapter 6 from our textbook, SQL for data analysis. So the first, I'm going to use the same information that is provided by the book. So first thing I'll do is I'm going to open the folder where I have all the information. You will find this information on Brightspace. You can download these codes. Chapter 6 Anomaly Detection. That's the folder. Okay, so here I have all I need. So I have 3 CSV files with the earthquakes information. And then I have a couple of SQL scripts. One to create the table, with all this information with these 3 files. And there are some queries for the SQL component. And of course, I have a Jupyter notebook for the EDA and the anomaly detection. So in our textbook, I have to say that the chapter it's even though the name is anomaly detection, I think it's more like outlier detection because it's more like the classical things that you will do with a single variable, right? But it's not for a multivariate analysis. So the statistical tools that are given are like the basic stuff. Okay, so let's load information. Let's connect to the database. So after we will need to create a database. So I'm going to PSQL, the user. So I'm going to use the Postgres user. And then initially, I'm going to load the Postgres database. It's going to request the password. So now here in Postgres, this is the database, right? That's the name of the database. So I'm going to create a new database. Let's create database, earthquake, semicolon. So now we have created the earthquake database. So we can now go or connect to that I'm working locally right now. So let's connect with the new database. Okay, so now we're connected to the earthquake database as user Postgres. So I'm gonna load the table. So let's go over this real quick. So this is a simple script. So it creates the earthquakes table. So here we have the different variables, latitude, longitude, we have the magnitude, right? And then we're getting this information from 3 files. So once you have downloaded the file, you will need to update the path. So I'm using my path here to get the data, but your path is going to be different, right? So please make sure that you right click the file and copy the path and update the SQL. I'm going to remove this and I'm going to write your path. So you need to update that information, right? Originally in the book, there are like 15 CSVs. I'm just giving you 3 because they have a different encoding, and I don't want you to get problems with encoding. So with these 3, you should be fine. There are like 300,000 observations, which is more than enough for our analysis. Okay, so every time you see these codes, like these commands like \copy, this is PSQL. So that's why I cannot run it from here. I need to run it from the terminal. Okay, so now let's execute the SQL file. So remember \i, the name of the file, which is create earthquakes. I'm just writing the name of the file because I am in that path. But if you don't know if your file is in a different place, you need again to copy the path, right? So be careful. Tables.sql. So it's saying that this file the file is not in the directory. So that's because I'm misspelling the name, right? So be careful. So it's without the S, table. It's a single table. So now that I fix the name, let's see now, it dropped the table, it created the table, and now it's copying, this is the first file, the second one, and the third one. So now we have this, the three CSVs have been loaded into our table. So if you want, you can explore, like the earthquake database, like select. So let's count like how many observations we have. So let's count from earthquake, that's the name of the table, and semicolon. So earthquake is the database. Be careful, that was my mistake. Earthquakes, plural. All right. So now it's telling me that there are almost 300,000, right? Which is fine. Now you can keep writing some SQL here, or the book provides all the examples in the anomaly detection queries SQL. So here you will find the basic stuff. So how to like number of earthquakes per magnitude. So let's go over the first two. So let's connect. Now my database is earthquake. There you go. So now that I'm here, and I double check here. So localhost earthquake Postgres, right? That's the user. Database earthquake that we just created. So we run this and we get the number of earthquakes per magnitude. So you see the distribution, right? So most of them are like, let's see, 4.8, oh no, 4.7, 3,000, 4.6, 3,500. So you can just keep looking, or you can create some histograms, which will give you, like it's a better idea to spot the distribution, right, of the magnitudes of the earthquakes. But this is just the SQL component, the SQL component. So here you have more specific queries this is for Northern California. Right? You can analyze the distribution. Since this is to find anomalies, but again in this case it's more like outliers in the context of the book. So they use percentiles, like to find a small percentile will give you an idea of some outliers, small values, or a high percentile, like percentile 99th. So if whatever is, like after that, most likely is an outlier or an anomaly, right? Okay, so you can explore, these queries. They are not that large. Or if you want, which I think is better, you can bring everything here to a Jupyter notebook. And here it's going to be easier for us to explore. Now it's important for me to disclose that for this notebook, it has like around 1,000 lines, a little bit more than that of code. This was a single prompt using a GitHub Copilot. And to be more specific, here I'm using a Cloud Sonnet. This is from Anthropic. So I'm using the agent mode, and with the agent mode, remember that with your university account, with your email, you can get the pro version for free of GitHub Copilot, and so you get access to the latest models. So at this moment of 2025, so you can have access to GPT and also to Cloud Sonnet from Anthropic. You have GPT-5 codex, which is good too. But I'm using Cloud Sonnet 4 or 4.5. And again, with a single prompt, I will show you what I got. So here, I get first like an EDA. So it connects, of course, the database. You need to, and this is important, to update your information here, your password. I'm using the same password in all the videos, right? sometimes with the uppercase or with lowercase. Okay, so once we connect, you can perform the queries and do the EDA, right? So in this EDA, you get an idea of the missing value. So we're missing for this variable the magnitude type, 19 observations. You can drop them if you want. We can create some summary statistics, for the magnitude, which is our key variable here. We can visualize, of course, the distribution of the magnitudes. So that we have a lot of information here, right? Because there are 300,000 observations. What else you can see here? So you get, this is the basic stuff. So you can standardize if you want within the z-scores, right? That's after this. So this is the EDA, correlation between depth and magnitude. It's like 0.3, yeah, 0.35, the correlation. For the anomaly detection, which is our, is the whole purpose of these videos. So the z-score, as I have mentioned before, is a basic statistic analysis or anomalies, to be more specific, outliers, like analyzing a single variable. So when you standardize a variable, now you measure the variable in terms of like how far is the observation in a standard deviation from the mean. So if it's 0, it means that it's right in the mean value. If it's 1, so it's 1 standard deviation above the mean. -1, 1 standard deviation below the mean. So typically you will find outliers or anomalies for z values that are greater than 3 or less than -3. Okay, so let's see the summaries here. So there are 0.35% of the observations are considered outliers or anomalies here based on this criteria. So we have 1,025 earthquakes, right? That where the z value is greater than 3 or less than -3. So here are the top 10 anomalies based on the z-score. So this one is 5.5. It's like, it means it's like 5.5 times standard deviations above the mean value. So it was a 9.1 earthquake, right? This is the great Tohoku earthquake, right? Okay. So you have some plots with these values. 3. They are also for 2, just to check potential anomalies. You get interpretation. Same idea with the IQR. This is more. Remember that this is used for the whiskers. So it's a different way to find the outliers. So using this criteria, this is like the box plot criteria. So we find 9.46% of the observations are considered anomalies or outliers based on a single variable. These are based on a single variable, right? So these are the points that are above and below the whiskers. Okay, so you can do a similar analysis using percentiles. You can find like the first percentile or the 99th percentile, and whatever is below the first percentile, that's considered like very small. But in this case, we're more curious about like what is above, right? Like very high, because we're talking about magnitudes here. So like small earthquakes is that's not relevant, to be honest. But like high magnitude earthquakes are really important. So you can identify extreme high or very extreme high, depending on the percentile that you use, like 95 or 99 percentile. So let's see how many of each we get. Okay, so for the first percentile, it's a negative value of the magnitude. I checked this, and it mentions that sometimes the values are really small because it's because of the tools, but a negative value means something really small. Like that's based on the sensors were sensible when capturing this. So it's not relevant. Again, what is really important is this portion here, because that's where you get, high or very high earthquakes. So in the very high end, we have 2,500 earthquakes, right, above the 99th percentile, and high 10 13,000. Okay? This is another way to visualize them, the earthquakes and the outliers or anomalies. Okay, so let's check the isolation tree. This one, the isolation forest method. So this is a technique that tries to split the observations, and if an observation is if one point can be found with a small number of splits, then it's considered an isolation. It's considered an anomaly. Okay, so we prepared our data, the variables, we scale the information, right? We standardize the variables here. This is very common, like when you're using machine learning algorithms, the standardization or normalization are very common with clustering techniques and some specific algorithms. So in general, it's a good practice. Now, a key parameter here in the isolation forest is the contamination rate. So here we're testing three values, 1%, 5%, and 10%. So the contamination rate, it's basically like what is the estimation that you have of the percentage of outliers or anomalies in your data. So in most of the cases, you won't know that. So you can use the default that's going to estimate that for you, or you can test different values. So here we're testing with 1%, 5%, and 10%. Because this will help the algorithm to use a threshold to identify the anomalies. Okay, so once we run this, we will get some scores, like anomaly scores, and also predictions of which observations are of each type. So from everything included here, the anomaly detected will change, of course, depending on the contamination rate. If it's 1%, it's going to find 1%. If it's 5%, it's going to find 5%. Right? So that's the number of anomalies that you get. And the nice thing about the isolation forest is that it includes other variables. It is for a multivariate analysis, but the previous statistical methods that we use, they were using only a single variable. So you are missing context, right? So in the isolation forest, you add context, you are more complexity in your analysis when you are finding the patterns of anomaly information. Okay? So these are the scores. So the anomaly threshold. So here you will get scored between -1 and 1. So the lower the score you get, then it's considered an anomaly. This is anomaly threshold. So whatever is below that threshold, then it's going to be considered like an anomaly. That threshold will depend on the contamination rate that you provide. I like this plot. This is for the distribution of the anomalies. So the red stars are the anomalies, right? But you can see them geographically. So you get some information about the isolation forest, and then you can compare all methods. So I'm not going to say that this one is better than the others. I guess that we need to kind of like provide a comprehensive analysis. So the basic statistical analysis is going to contribute to the isolation forest and other techniques that you may use. So key lesson here, remember, outliers are not always the same as anomalies. The concept of outlier is way more basic. It's like for a single variable, like one dimension analysis. Anomaly, it's for multiple variables. It considers also context, right? I highly advise you to go over the video where we discuss a little bit more about anomalies, the type of anomalies, and the algorithms that you can use here. Okay, so I'm gonna stop everything for now. I'll see you in our next lecture.